Oh, what was it? Here we go. Nope, wrong one. It's the one that says notes. Notes. There we go. Okay, so with your homework out, just real quick, go down your first worksheet. See if you got whether they were an element, a compound, or a mixture, right? That's the front side. The back side, I used an E for heterogeneous and an O for homogeneous. So check that. And then matching the 6 pictures to the elements or the chemical formulas. Please double check and then ask any questions if you got one wrong. So check your work right now. It's okay to get something wrong, especially a couple of them weren't very clear at all. Like coffee instead of a cup of black coffee, you know, they weren't very clear. So double check and ask questions on being able to classify mixtures. And just be putting your homework away, and that'll signal to me, that you're done with this. And everyone, please get out their lab books. Okie dokie. So today we're doing 3 different lab investigations. Not we, you are doing 3 different lab investigations. So you will literally use 3 different pages in your lab book. That's what I'm looking for, 3 separate pages. In your lab book. So let's do the first page in your lab book. Let's pretend this is the page in your lab book. So today we are working on separating both compounds and mixtures. So the first page, we're going to start with separating a mixture using chromatography. So separating a mixture using, nice and big, chromatography. So that is your title. Now, remember what a mixture is, right? A mixture, we have compounds physically mixed together, compounds, different compounds mixed together. More complicated than this, less complicated than this. That's a mixture. Now, you're actually going to separate ink. You're going to separate ink, which is a homogeneous mixture. And all separation techniques are based on either chemical or physical properties of the matter. This one, we're going to use the physical properties of these molecules to separate it. And the physical property we're going to use is, it's hard to explain because we haven't covered it yet, but polarity, how polar something is. And that goes back to the concept of like dissolves like. Okay, so if you were to rub your hands with butter, right? Nice butter, get it all over your hands. You can almost feel it, right? Rub your hands with butter and you go to the sink. Can you wash it off with just water? No, because they're not alike, right? The cold water or warm water won't get the butter off your hand. The butter is not polar and water is polar. So the only way to get the butter off your hand is to use something like it. So you use soap. Well, soap is not polar. So it's like the butter being not polar. And you use soap and then the water is kind of a physical rinse. A physical rinse. So like dissolves like. We're going to separate the ink mixture by dissolving in like, right? So I've chosen a Vis-a-Vis pen, and it's specific to Vis-a-Vis because it is a polar ink, a polar ink. So the ink is polar. The ink is polar. But all the molecules within the ink don't have the same amount of polar. So polar can be in degrees. There's this gradient of polar, okay? And that's how we're going to separate it out. Some are really polar, and some are, take it or leave it polar, right? So we're going to separate the ink based on the physical properties of polarity, like dissolves like, using chromatography. Now, you have the little kind of top section. Take up this little top section. So include notes on chromatography, draw and label a setup diagram. This is okay. So the setup diagram that you're going to have is you have a 1,000 ml beaker. So you're going to have a 1,000 ml beaker. Let's see, 1,000 ml beaker. So you don't just say beaker, right? You don't say 50 ml beaker. You say 1,000 ml beaker. Which means this is a 1 liter, right? 1,000 mils is 1 liter. And that kind of makes sense because if I put another one on top, doesn't that look like a 2 liter bottle of soda? Right. And 1,000 milliliters. So a lot of milliliter. Very good on 1,000. Okay. Then you'll have a piece of chromatography paper. Looks like this. Chromatography paper, notice I'm holding it by the sides, is what's called the stationary phase of the separation technique, meaning it doesn't move. Right? This is the stationary phase of the separation technique. And what you're going to do with your chromatography paper, first, don't get your greasy hands all over it, right? Because that is, the oils from your hands are different than the ink, right? These are non-polar. Your oils are non-polar. You need a super sharp pencil. Super sharp pencil. And the one end of your paper, you're going to first give it a little point, with some scissors. So let me show you. We're going to give it a little point. Let me get a black background. I'm going to give it a little point, not an extreme point, but just a little point like that with your scissors. Everyone good on that? And then using a ruler, which I left over here, we're gonna come up approximately, are you guys writing this down? Approximately a centimeter, not in, let's say right about here. So how do we want to look at that? We can say a half a centimeter from that point, right? But approximately, let me see if I put it back on white. There we go. About this far from the top. So 1.5 centimeters from the tip, right? Super soft, sharp pencil, not heavy. You're gonna draw a nice light line from end to end, right? Don't gouge it. Don't gouge it out. Everyone with me? Now, we're separating vis-a-vis ink. So here's our vis-a-vis ink. Now on that line, I want you to think of it as the diameter of a circle. Okay. And the size of your circle is kind of the size of a hole punch. Okay. So what you're going to do is I'm patting this around. I'm not drawing the circle. I'm not rubbing it. I'm patting this. I'm giving the paper time to absorb the ink, and I'm making it about the size of a hole punch. Right. So I'm tapping it, and I'm making it about the size of a hole punch. There we go. How are we with that? Good. So that's kind of the easy part. Yes, it bled through. That's fine. Kind of the easy part. So you're then going to set your paper up so the tip, see how it's kind of curved? So you can always kind of bend it a little on the sides to kind of straighten it out. You want to have the tip just touching the bottom. And that's what your ruler's for. The ruler's going to sit on top. And once the tip is just touching the bottom, squeeze it against your ruler. And then bend this over your back. You don't need to tape it. It's gonna sit on top. Just like that. Now, there's going to be 2 of them in here. Why is there going to be 2 of them? Because every student needs their own chromatography paper. So even though you 2 are a group, you're doing 2. Okay, you're doing 2. Now notice there is no water or anything in my beaker yet. Okay, there's no water or anything in my beaker. Once you get this set up, you'll have 2 of them. Just take it out. You're going to fill no more than to the 100 ml line, no more than the 100 ml line, because you don't want the water level to hit this ink, right? So this guy is hanging out right above the surface of the water. So you want the surface of the water kind of where the ruler is. The most important thing is that we don't splash this with water, right? The water is going to be pulled up by the stationary phase, and it literally needs to pick up the ink in a single direction, okay? So if you splash it or anything, it screws the whole thing up. Also, you can't have anything touching the sides of the paper. So it can't be against the glass, Can't be against the glass in any way. It needs to, and it can't be hitting the other paper. Right, so you need a nice clear column, super clear column. So you can just use water out of your tap. And you know these sinks are all kinds of cray. Not much. Yes, it's splattered on the side, so I got to make sure it doesn't touch the side. Good. Whoop, hold on. I'm going to do a time lapse. I like time lapses. Do you guys like time lapses? Yeah. So not slow-mo, but I'm not going to get that confused. That is so anticlimactic when you do a slow-mo and you thought it was time lapse. It's like the worst. Okay. So I'm doing a step. Okay. Okay. So the water's traveling up. The water and the ink are called the mobile phases. They're the ones that are going to travel. You guys rake leaves? Okay, so there are two forces going on here. If you have a pile of leaves over here and you pick them up, that's what the water is doing to the ink right now. Right, so you have a big pile of leaves. And then it's traveling and the paper is trying to grab onto the leaves. So the paper is grabbing. So as you walk, the ones you have a tighter hold on that are more like water, the leaves you have a tighter hold on, move further with you. The ones you have a looser hold on, they fall, drop, right? So I'm dropping, and the amount of leaves I pick up is not the amount of leaves that make it to the trash can, right? You've lost some along the way, the ones you didn't have a good hold on. So if the molecules did not have a strong hold with the water, like dissolves like, they will drop off on the paper like gravity. So we're separating based on how much the pigment molecule is like the water molecule. The water molecule being very polar. So we're separating based on polarity. Does this make sense to everyone? Okay, so you're going to set yours up just like this. I'll give you 20 minutes, no more, because we got 2 other labs to do. There are 2 rulers. You only need 1 to run the test, but at the end, we're going to calculate retention factors. So both numbers will need a ruler. You got your scissors, you got your beaker. You can do it at the lab, you can do it at your desk, doesn't matter, right? Just like it's sitting right here. Here are the chromatography papers. They're in stacks of 10. So 10, 20. I have had them flattening in this big, heavy textbook just to make them as straight as possible for you guys. 10, 20, 30. Again, when you grab them, keep your hands on the edges. So you'll get your papers, grab your beaker, go work wherever you want, get it all set up. And in your beaker is the this. We got 20 minutes. So we got here before 9. Yeah, every person needs their own chromatography paper. You're gonna use 2 in 1 beaker. We're using a beaker that large, so we have a long space. Please sharpen your pencil before you draw that light line.
We have to make the line.
Yeah, it doesn't have to get to the bottom. What it has to do is.
No more than we're gonna do calculations when it's done. Not right now. You have the top parts. You know what chromatography is? Remember, your lab book is a resource for you. You're supposed to do a diagram of the setup.
Oh, very good. Yeah.
Very good. Very good. Nice. You're just gonna have yours over. Get some water in
Yeah.
Or you want some water moving on it's great.
It's a garden.
We have yours. too low. Oh, see how the ink's going in there? Where you guys want me to get it? No, it's too late now. See how the ink is actually in. Right? Oh, yeah. You're gonna need it. Calculation. There are two in each speaker. So that it's easy that you get confused. Okay, so return to your seats, guys. You got a second lab. On a new piece of paper. In your lab book. Oh my goodness, put that away, please. In the lab. You're not doing anything except for switching to the next page in your lab book. Flip the page in your lab book. And so if we look back at our card, we've got this guy running. So we have two other separation techniques. So we're going to have two other pages. Who wants to do electrolysis first? And who wants to do distillation first? Okay, distillation wins. So on the next lab page, distillation is a separation technique. And it is to separate solutions. To separate solutions. Okay. Now, what you guys will do over here in the hood, and we trip over the luggage. We have a distillation setup. We're distillating or distilling Mountain Dew. You need to come over here and you make video or whatever you want to do over here. First of all, don't touch anything in here. This is 18 molar acid. Don't go near it. Right? There is a piece of paper here which will tell you what you need to do. What's going on is I'm running cold water through this tube into a piece of glassware called a condenser. What's the root word of condenser? Condense. What does that remind you of? The act of compressing, that's one. What about a change of state? What? Condensation. What is condensation? Condensation. Gas to a liquid, right? So you have a nice cold soda, you go out on a humid day, the humidity from the day sticks to the outside of the soda, right? That's condensation. Where'd that water come from? Your can's not leaking, right? It came from the air outside and it condensed on that surface. So this is the condenser and we're running cold water through it. Cold water goes up and then it comes out. You can literally hear it running back into the sink. So a lot of cold water is going through right now. Here's a hot plate. I got the hot plate on. I've got a closed flask. Right, so normally you don't heat up a closed flask because it'll explode. But I have two open valves that are allowing gas to go through here. If I'm heating a liquid, what's gonna happen to the liquid? Yes, it's gonna become a gas. Somebody said boil. That's good. We're separating by boiling point. See any bubbles? Coming up here? Yeah, you see bubbles? And then you can read the temperature. Now, water boils at 100. But the temperature right now is 62. On the thermometer, 62. Tons of bubbles coming out of the liquid. What do you think that is coming out of the soda at 62? Somebody said it? CO2, bubbles are coming out. So we're first making this a nice flat soda. We're first making it a nice flat soda. And it's hanging out still in 62 for a while until all that's gone. And the next thing that comes out should be the apple flavoring at a much lower, right? Much lower boiling point than water. So I'm letting the so we're coming up near 70. Once we have hot vapor coming through here, when hot vapor meets cold vapor, it's going to condense, right? Then it'll run down this tube into the beaker. The beaker holds distillate. Distillate, that's what you call it. So it's going in as Mountain Dew, it's coming out as distillate. Sound good? We have this, it tells you what to put in your lab book. You're going to check this guy out. And on another page, you're going to check out the Hoffman apparatus. This tells you on your third page title, what to do. And you have to look very closely to see what's going on. Look very closely to see what's going on and answer questions. There's also notes here. All of that while also watching your chromatography. So you're balancing three things. You made video, take these guys and watching them. And use that for information. This is plugged into the wall. Now, chemistry classrooms are notorious in the media for fire accidents. But really, globally, what kills students in science classrooms is electricity, and it's usually in a physics classroom, right? So this is literally plugged into a wall. Should you touch the wires? Good with that? We'll touch the wires. Good. Yeah, okay. Work manual and try to figure out these separation techniques. Okay.
And let me know as soon as distillate starts coming out of there, I'd like to separate it. Okay. And then A4, I need to add materials, add a file, attach a file, unit 3. This guy. Oh, it's not letting me do that. Okay. Cancel. Cancel. So I guess I'm gonna have to go to YouTube.
When German,
You need to go to my channel. I'm gonna need to. Videos. Need to upload. Videos. Video. File. Boom. Open. Detail. Yes. Celsius. Temperature is always in Celsius. Absolutely. These look really close to the anode and cathode. And record the volume of gas in each of the tubes. Obviously, the volume is changing. Do we have any distillate back there?
Yeah.
Yeah?
Separated. Right. That apple flavor, very first, that it gives you the cherry. The cherry that comes out, will sneak up in the very first drop. Very aromatic. Because it's separating the compound and scents are more volatile, meaning the gas rates are more volatile. Water in the bottom here. Water comes in and it's surrounding it. Very much you drop the Yep. The first two things out. Don't touch it. Distillation?
Is that going in this?
Yep, in the bottom of it. Yep,
And then where's the coffee?
that's coming out of the tube here, right? So
So
it's,
it's this.
yep.
Okay.
Yep.
And this is the.
Yep. What's the point of that? Okay, let's go look. Hey, what's up?
Yep, it's being plugged in. Electrolysis. You do electric device. So. Cold water is going to be. Need a bigger here. Start next to the. Right in there. And the wrong is the rain. That's running when I'm outside. The inside of it too is really hot. Inside of that, then it's not. It's surrounded by cold water. So we call it condenser. Forcing this index. It's not this paper going on. What's the events here? And then it's the rain around. It ends up here. And that is. Water was in the gas. The purpose of this is for the installation force the condensation from the steam. We don't want to steam it. We want to make sure it all gets condensed. It's going right in. So cold water. Cold water. Water's on. So no water is running through here and it's slowly heat up. It's not. But if I run close. The water will move. It's not a secret, it's not aware of us. And it's building them out. Inside here, like warm paper. And then we're raising. Raising it here. And then the blue one all around here. Working that will be very condensed. Building up on the top. Don't leave it down here. And then all of this. Now it's like, build it up. Yes. Gas and bubbles that pop into. So these little bubbles are traveling to the surface, and like this is surface of the liquid, then pops. Pretty normal words. And that fills this chamber. Right? Yep, so these little bubbles come up, and at the surface they pop. And they fill this chamber. Yeah. Right? Yep, because you're measuring the gas, not the liquid. Right, it's the gas. So, obviously, the bubbles are still forming. If it's hard to read, take that dial right there. On the right, and turn that. The black dial. 14. All the way, there we go. So that will keep it from moving. And you can. So. Surface. Now you may wonder when your chromatography is done. And we're waiting for a blue butt. I know, it's strange. But everyone's will end with a blue butt. You got a little blue butt? It is a light blue, otherwise known as aqua. An aqua butt.
Weren't they the two separate chambers in the electrolysis? And what is why is it not just one where it happens? Why is it two separate areas?
Okay, one has an anode going to it, one has a cathode going to it. So when you split water, what are the two things we're making,
Hydrogen.
right? So, one side is collecting one gas, and the other side is collecting another gas. It's called a Hoffman apparatus, because Hoffman created this specifically for splitting water.
Okay, that makes sense.
Oh, sorry. Milliliters.
Not that you're doing this now, but your chromatography will run, everyone look front, until you get a aqua blue butt. Everyone should get a butt like that unless you had trouble starting. You're going to use your ruler and you're going to mark the highest point the butt went lightly with pencil. Okay, lightly with pencil. This is still kind of wet, but the highest point it went, you're marking lightly with pencil. Everyone understand what they're gonna do? When you take yours out, you can set it on a paper towel for a second before putting it on your paper in your lab book. You're gonna use the ruler while it's still wet to mark the highest your boundary traveled, the highest part of the butt. And you're just gonna lightly put a pencil line across the furthest it traveled. No, that's not it. That's the first step. That's the first step of many. So is there a way I can have your attention? Is there a way I can have your like undivided attention? I'll go through what to do and then you'll have the rest of class to do it. Okay. So you're gonna take your guy out. Once you have this butt, you're gonna mark the highest point with a pencil. Step one, pay very close attention. Step one, using your clear ruler, you're measuring the total distance. Listen carefully. This is the distance between your two pencil lines. You have a pencil line here and you have a pencil line there, and you're measuring in millimeters. So step one, I'm measuring in millimeters. So this is 100 millimeters, 101, 102, 103, 104, 105, 106. It's not quite 107, so I'm at 106.7. I'm going to call it 106.7. So 106.7 millimeters is the total distance the water traveled. For me, it will be different for everyone. Does that make sense to everyone? Now, you should be able to discern, and this camera is not great, multiple colors. I definitely see a region of yellow. You also might want to think of this in halves, right? That might make it easier for you guys to think of it in halves. Yeah. So I have a region of yellow, and if I were to lightly circle the yellow, it has a weird kind of shape, kind of goes up and down. With your pencil, you'll lightly circle the yellow, and then you are to estimate the center of that yellow with a dot. You estimate the center of the shape you make. You estimate the center of the shape you make. Does that make sense to everyone? So this is the average the yellow pigment traveled. So from the center dot to my starting dot in millimeters, that's 10, that's 11, that's 12. I'm going to say 12.9 because it doesn't look like it's just hitting 13. So 12.9 millimeters is the distance yellow traveled. To calculate the retention factor, I'm going to do 12.9 millimeters over the total, 106.7 millimeters. My millimeters cancel, so retention factors have no units. Retention factors have no units. I'm dividing a number with 3 sig figs by a number with 4 sig figs. How many sig figs are in my answer? 3. So 12.9 divided by 106.7, and I get a retention, R, capital R, lowercase f, lowercase y for yellow, equals 0.121. That is my retention factor for yellow. Does that make sense to you guys? You will do that for every color you see. There is a pink. There is, traditionally, you should see a red heart, which I always thought was kind of cool. You should see a red heart in there. You then have a purple zone, a dark blue zone, and obviously you got your aqua butt zone. Either one of these, you estimate the center of that aqua pigment and you measure from where it started to where it goes. Retention factors are ratios of how far the pigment traveled versus the total in millimeters. Now, it's wet, you can't see it too well. You can wait till it dry. Everyone is to tape this into their lab book. It's going to have pencil marks all over it, and you will calculate the retention factors for all colors. Now, if you do it right, everyone should get the same retention factor. These numbers will be different. 100%, these numbers will be different, but your retention factors should be the same because you use water and you use the same ink. This is not like different for each one. This is the same retention factor for the yellow pigment as it is across the world. Yes, sir.
I was right. That R.
This means yellow. R sub F means retention factor. Then you have yellow. You could write out yellow. You're going to have pink. You might say magenta. You're going to have red. You're going to have purple. You're going to have a dark blue. You're going to have an aqua. Yes. Your yellow going this way, your water started here. Think about what's going on. It picked it up here. It picked it up here. So this is the lowest you can sketch your middle. You're going to not do this because these forces are not based on polarity. They're based on the amount of hydrogen bonds in the liquid, right? The water, if you did it right, it picked up the pigment here and traveled. So you're going for half the distance traveled. Half the distance traveled is midway from your, is the middle of your shape. Half the distance traveled. So these leaves fell first, right? This is where you pick up the big pile of leaves, and these are the ones that fell first, did not have a good hold, right? They dropped off and hit the ground first. Then these leaves, then those leaves, then those leaves, those leaves. Okay. Now, you know how you found everything over there? That's how you leave everything. You don't have to dry your beaker, but the scissors, the two rulers, and the pen goes in there and you line them up on that counter.
We're measuring the colors. I didn't catch it. Do we measure starting when that color starts and then we start from the bottom?
The bottom.
Bottom. Okay.
Yeah, you're always going back to
So always
this.
starting at that bottom line
Yes.
up to the end of that color.
No,
Or-
to the middle. You estimate the middle.
Okay.
Right? So the idea is it's half the distance traveled by the pigment.
Okay.
Okay, so you circle the whole pigment
Mhm.
and then you estimate half of that or the middle of that shape.
Okay.
right? So you're gonna have like a red heart, you estimate the middle of that heart,
All right, and then you measure from that line.
from
up to
this
that
line to the middle,
line. Okay.
to the middle of the heart. So it's always, you always start from where it got picked up
Mhm.
to where it got dropped,
Okay,
right?
that makes sense.
The leaves are picked up here and the red leaves fell here,
Oh, okay.
right? All of it got picked up here. The yellow leaves fell here. Your pink leaves fell, so measure from here to here, and that's where your pink leaves fell,
Okay,
right? And then your purple leaves went from here to, let's say there. You estimate the center, and it's
okay.
from here to here. So you're measuring how far they traveled divided by the total distance traveled.
Oh, okay.
I have a question. Is it okay if we cut off the?
Yes, I actually tore it off.
Great.
And then you have a place to put tape to tape it into your book. Yes, let it dry some. Let it dry some. If you can't tell the difference in your colors, let it dry some, but mark the total distance traveled now. Mark, no, you didn't.
Oh,
It's the very top of the button,
yeah.
all the way across. That needs to be marked. Because that's how you measure from here to here. Right?
Uh-huh.
You gotta measure from here to here. So I need to see that.
Okay. And then, my, like red, since it travels down the sides,
That's,
I wouldn't count that.
no, so this is a different pigment. This is pink. Right?
Okay,
That is pink. Your red is like a heart,
okay.
right? Your red is like a heart. The sides here are pink. That's why I said you can also kind of look at it,
Like,
right? So you've got a yellow pigment, you've got this big area for yellow pigment, but you're estimated half the distance it traveled. So from here to there, half is like there.
Mhm.
So that's your half the distance the yellow traveled. Your pink kind of started from here to here, half that distance is like there. So this would be your pink,
Okay,
right? Your red, it started here and it's right about there, half the distance traveled, right?
do you see purple?
I do see purple. That's kind of like here,
Okay.
and you might see it too once it
Once
dries a bit. Mhm. Purple, dark blue, and aqua. So you're gonna have yellow, pink, red, purple, dark blue, and aqua.